But here in the nucleus are other particles with no electrical charge called neutrons. Very important characters too, as we shall see.
Thanks to Moseley and Rutherford, it was now known how many protons were in each atom. And since a proton is just a hydrogen nucleus, in theory we could just multiply the mass of the hydrogen nucleus up to get the mass of every other element's nucleus. But that didn't work. Most atoms were found to be around twice as heavy as the mass of their protons. This implied there must be another type of particle in the nucleus. Rutherford had previously attempted to explain this in 1920 by describing clusters of protons with electrons bound to them in order to balance the charge. He suggested that atomic nuclei were built from these clusters. He also described an atom of mass 1 which has zero nucleus charge, which was formed from the coupling of one hydrogen nucleus, aka a proton, with an electron. This idea of nuclear electrons was fiercely debated throughout the 1920s. One big issue with this idea was that if we know an electron is confined to a region the size of an atomic nucleus, this gives us a high certainty of its position, so according to Heisenberg's uncertainty principle, the certainty of its velocity will be very low. This means when electrons are emitted from the nucleus, as they are with beta radiation, they should have a broad range of kinetic energies, including energies that are much larger than what's actually observed when beta particles are emitted from the nucleus. In 1930, Walter Botha and Herbert Becker bombarded samples of beryllium, boron, and lithium with alpha particles, and they noticed that this caused the samples to emit an unusual form of radiation. It was unaffected by electric fields, meaning it must be uncharged. This initially led scientists to think that it was gamma rays, but they quickly noticed that this new type of radiation was much more penetrating than gamma rays were. 2 years later, in 1932, Irene and Frédéric Joliot-Curie noticed that when this new type of radiation was directed at paraffin wax, it caused the wax to shoot out very high-energy protons. It was soon realized that since gamma rays are waves, not particles, they would need to have a ridiculous amount of energy if they were to knock a proton out of an atom in this way. This indicated that some kind of heavy particle was colliding with the proton instead. The Joliot-Curies would go on to win a Nobel Prize for their work on induced radioactivity. Fun fact, these two were the second married couple ever to be jointly awarded a Nobel Prize. The first married couple was Irene's parents, Pierre Curie and Marie Skłodowska-Curie, who won their joint Nobel Prize for their own work on radioactivity. Here's another fun fact. Marie Skłodowska-Curie was the first ever woman to win a Nobel Prize, as well as being the first person to win a Nobel Prize twice, and the only person to win a Nobel Prize in 2 different scientific fields. So this was a pretty impressive family. News of the Joliot-Curie experiments quickly reached yet another of Rutherford's students, an English physicist called James Chadwick, and he got straight to work recreating it in his own lab. Not only was he successful, he was able to measure the speed of the emitted particles, as well as the inexplicably large amount of recoil they caused when they collided with other atoms. In his preliminary paper, Possible Existence of a Neutron, he said that his results were difficult to explain if this was gamma radiation being emitted, but the difficulties disappear, however, if it is to be assumed that the radiation consists of particles of mass 1 and charge 0, or neutrons. This explained the high recoil of the atoms they collided with, since an uncharged neutron would not be repelled by the nucleus it's approaching, and therefore it can collide with a much greater impact than a proton would be able to. A few months later, he followed this up with another publication, The Existence of a Neutron, where he confirmed his findings. With some careful experimentation and thorough calculations, he was able to determine that the neutron had a relative mass that was slightly higher than that of the proton. He said, allowing for the errors in the mass measurements, it appears that the mass of the neutron cannot be less than 1.003, and that it probably lies between 1.005 and 1.008. Such a value for the mass of the neutron is to be expected if the neutron consists of a proton and an electron, and it lends strong support to this view. This work disproved the existence of nuclear electrons, and therefore scientists came to realize that beta particles must form in the instant that they're emitted. What they deduced is that they form when a neutron splits to give a proton and an electron. The proton stays in the nucleus, which is why the atomic number goes up by 1, but the electron is instantly emitted. 3 years after these publications, Chadwick won the Nobel Prize for his work. With the discovery of the neutron, the full structure of the atom had been discovered, and the world would never be the same again.